Hello, everyone.
Hello. So, welcome to this interesting talk, the curiously recurring pattern of couple types. You may notice that we are two on the stage. Adi.
Yeah, and Björn. And actually, Björn is going to start, so I'll just
Right, sure.
join you guys.
So, I won't bore you very much with the background. You can read my name, Björn Fahller. I'm doing primarily C++. I live in Stockholm. Fairly active in the Stockholm C++ user group. So if you go there, get in touch so we can geek out. On to the topic. What I'm going to talk about today, me and Adi, is primarily concerning those of you who program in languages with static typing, and preferably with, for some definition, sane type systems. Sanity can be a gradual thing. Also, a curious thing about this is that we're going to tell you things that you already know. And despite this, we really think that we're going to change the way you view API design. So, without further ado, let's dive into some examples. A number of examples here. So we have a 2D space, a plane, and we have a vector on the plane. A vector really only has two properties. It has a length and a direction. We can add another vector to here, so a different length, a different direction. Where they are placed on the plane doesn't really matter. It has no concern whatsoever. So changing this it looks different, but it's not really a difference what it represents. It's still the same two vectors, V1 and V2. But this representation makes it easier to talk about addition, because we see addition of vectors as just attaching them tail to nose, and getting the result from the tail of the first to the head of the last. And you know this, right? We can negate a vector by just swapping its direction. We can move them around, as I said, and we can get the difference between two vectors by adding with the negation. Nothing new. And we can multiply a vector with a scalar to extend it or shrink it. It only changes its length. It doesn't change its direction. Multiplying vectors. Utter nonsense. Doesn't make sense. Not in this universe. And then we can have positions on our plane. So we have a position P1 and another position. What can we do with those? Well, we can, for example, subtract them. And the difference between 2 points is a vector that gets you from one of the points to the other. And likewise, if we have another vector, V2 here, and can add this vector V2 to P1, and we get to another point. So a point plus a vector is a point. Point minus point is a vector. And point plus point is nonsense. It doesn't make sense. At least not in this universe. So let's forget about vectors and points and 2D planes for a moment and have a look at time. So this is my showing off my extremely good skills at graphic design. This is supposed to represent a clock phase. So we have a point in time. It's what can it be? 4 minutes past 6, roughly, something like that. And we have another clock phase showing another point in time. So what is the result of subtracting those? What's the difference? Sorry, I heard a duration. Yes, so we have the amount of time that has passed from one of the time points until we reach the other one. So it's a duration. And if you're C++ developers, you know the chrono library where we call these time points and durations. What about adding time points? It doesn't make sense. We cannot do that. It's a meaningless thing. What is a 6:15 plus 7 o'clock? I cannot comprehend that. But we can have a duration plus a time point and get another time point. Because that makes sense. So 4 minutes past 6 plus 8 minutes. Yeah, that makes sense. I can see that. C programmers, pointer arithmetics, the source of absolutely no problems ever in software development, right? So we have an array of A's. Doesn't matter what A is, it's completely irrelevant. But we can have a pointer P1 that points into the array. And another pointer to somewhere else in the array. What's the result of subtracting them? What is D? In the C standard library, the type of D is ptrdiff t, which is an integer, which is interesting in itself, but let's not go there. What D is the distance, the number of times you must increment the pointer from P1 until you reach P2. And of course, we can go the other way around. Well, okay, we can try to add pointers. What does that mean? Not much. It's a nonsense operation. We cannot add pointers. But we can subtract a distance from one pointer to get another pointer. And this is curious, I think. This is really curious. Because are you seeing a pattern? I've talked now about 3 completely different things, but do you see a pattern? Because I did. I was working on a small C++ type safety library to make it easy to express safe types, strong types, that only allows the conversions that make sense. And I had seen this pattern repeatedly in the code I was working with. And I wanted to model this in this library, but I didn't know how. Or actually, I knew how to model it, but I didn't know what to call it. And then comes Adi, my co-presenter. So he introduced me to this YouTube video and the idea of affine geometries, which is exactly what this is. So the 3 examples I showed you with a 2D plane doing vector arithmetics and points, and the chrono with time points and durations, and the pointer arithmetics in arrays, they are all representations of an affine space geometry. They're all the 2 latter ones are one-dimensional geometries, and the plane is a 2-dimension, but it's the same principle. So I have Adi to thank for finding the name for this so that I could add it to my library. And with that, I hand over to Adi.
All right, so I'm actually a computer vision developer. I do a lot of geometry, and I came around to noticing this same pattern through my work. And I think a lot of the number system and type systems or fundamental mathematical systems that we commonly encounter are what's known in mathematics as monoids. They're generally closed under some operations. It's always an integer plus an integer will give an integer. Usually the operations take two arguments of the same type and return, and the result is always the same type. And I suddenly noticed the same patterns that Bjorn was mentioning, where we have a very interesting interaction between two distinct types that has some very interesting behavior, and it turns out that this behavior is actually very well defined and very well known for at least 200 years in math. And all you have to do is just identify the term. And I think I was curious about this, and somebody on Slack happened to just mention the name, and I started digging and came across what we're going to see today. And although we will get into some mathematical terminology, we're not going to, this is not a math talk, because I think the important thing to take from here is how to do API design, how to design your fundamental types so that they save you from yourself. But before that, let's talk a little bit about affine spaces. And affine spaces generally have, intuitively, they have two distinct types. We have a point, which, as we saw in the examples before, it can be some kind of position. Maybe it's specified with coordinate values. The actual internal representation doesn't necessarily mean, isn't really related to the behavior itself. So it might have different types of representations, but we can think of points as locations or addresses or indices or any kind of thing that represents a position. The second type is a vector, which behaves basically as the normal linear algebra 101 vector, and it's defined as the difference between 2 points. And it's often referred to as a shift in 1D often, or an offset or displacement, or when we're talking about time, we may call it, the English term would be duration. But these are all different names for the same mathematical object that the vector represents. Now, I mentioned that the internal representation may change. So we might think of a point as implemented internally as some kind of origin plus an offset. However, point is still not, even though we have this internal representation, it doesn't mean that a point is a vector. It's a totally distinct type, and it defines totally different behaviors. Now, let's look at some more, at some definitions. So, as we said, the affine space, it has two types of entities, the points, vectors, and of course scalars, because now the vectors are a normal vector space. Anyone who's taken any linear algebra, you know we have closure under usual operations like addition, subtraction. We can multiply by the scalar, and we can do linear combinations, just like any vector that I'm sure many of you have already implemented or used whenever you're doing graphics or gaming or anything to do with multidimensional data. And the affine space adds these additional following properties. And it's exactly the ones we saw before. I'm actually not showing you anything that Bjorn hasn't shown before, that given 2 points, P and Q, the difference between them is the result, or I want to say it, because this is a talk about type design, the input types to the subtraction operation are points, and the result type of the subtraction operation is a vector. So we're actually seeing the interaction between two different types, and the vector is defined as the difference between 2 points. And similarly, we can apply the addition operation between a point and a vector, and the result is another point. So if we're familiar with the normal vector space, this is slightly a more general concept where we have this interaction between points and displacements. And these are the type of examples that we're going to see. The interface, I'm not sure, how many of you here are C++ developers? Oh, wow, I'm impressed. Great, so most of our examples will be from C++, but I do want to emphasize that everything we're talking about here has nothing specific to do with C++. This is about type design. And the vector operations on the left that we can see, we have the addition operator, which takes two types. This is an infix notation in this case, and the result is again a vector. We have scalar multiplication on the left and on the right, and we have the two syntactic sugars of a vector subtraction, which is basically like multiplying by the negative, right, and negation. The affine operations, as we mentioned before, they take two point types, return a vector type. We can define addition of a point with a vector, getting a new point, and again a syntactic sugar of multiplying that said vector by -1, which gives us the negation. Naturally, we can also define for the left side, we can also have the mutating versions of plus equals and multiplication, in-place multiplication. Now, let's go back to the examples that we just saw and see how these things are actually already implemented. That's why we're saying we're not going to teach you anything you don't already know. We were very surprised to identify this feature, which is so ingrained into what we already know, but nobody actually gave it the proper names. So here's an example for chrono. We can see on the first line, we can take the start time, we can save it in the beg, and then end is after some time, we have the end time points. So begin and end are the time points, and the difference is saved in the variable dur, which is not a time point, it is actually a duration. And then we can define, we can do some time or chrono arithmetic. We can take the begin, add it some kind of duration, and maybe 1 millisecond less. That 1 ms is it's a standard literal for millisecond, and almost is just before the end. And we can, as we can see, we can use scalar multiplication of dur is a duration, and add that to, this is a point plus vector, so the result is another time point. One interesting example, just if you guys are interested, that C++20 is actually bringing chrono into the calendar. It brings calendars and multiple clocks. So in this case, UTC clock now is going to give us not the time where the machine is running, but actually the time at Greenwich. So this is a different clock than what the system clock would have given. And now UTC now is still a time point, but it's actually templated on a different clock, so it's a different type. So if we look at the UTC next, and it's assigned UTC now plus 2 times duration, that's okay, because the duration is still universal in between these two clocks, because we're, let's say, still on Earth or still moving at liminal speeds. However, when we try to subtract UTC now, begin from UTC now we're trying to apply a subtraction between points from different types, and this is not actually going to work. So this is one extra level above that C++20 chrono gives us, that we can't subtract 2 time points, which are 2 separate types. So again, the type system is saving us from ourselves. Now let's see an example of iterators. So we have a vector called vec, 4 elements. And again, beg is begin, end is an iterator to the end. I remind you that early versions of the STL actually implemented vector iterators as pointers. So this example is almost identical to the examples that Björn showed us earlier, where we have an array and we have some pointers pointing into this array, and we're doing some basic pointer arithmetic. But in this case, we're actually using iterators, which sometimes may be implemented as actual pointers, but they don't necessarily have to be. And we can see that count is the sub end minus begin, gives us the number of elements or the displacement that one iterator needs to go through to go from begin to end. Last is the one before that, and neg is actually the negative displacement. So this is an interesting fact that we can see here, is that displacements are almost always signed, or in general they are signed. It's fine to say that we have a negative displacement between end and begin, and a positive displacement between begin and end. So you might say, well, you know, vector, it's just an abstraction over an array, and these are just like C pointers. But what about associative containers? So let's see an example. We can have an STD set, which is an associative container. Essentially, conceptually, it's a sorted range, and it has some kind of order of less than, let's say, the default here. So, and it has 4 elements, 0, 1, 2, and 3. And again, you can see there is exact correspondence between the rows on the right and the rows on the left. So begin and end are the begin and end. However, because STD set doesn't provide random access iterators, we cannot actually, the iterators themselves are not, they don't have operator overloading for addition and subtraction, because these are required by the standard to provide certain complexity guarantees. However, conceptually, or at least mathematically, we do have the exact corresponding functions that give us the subtraction. So we can see that STD distance is really equivalent to having a iterator subtraction to get the displacement between the end and the beginning. Similarly, STD next is just is essentially the same concept as the addition of an iterator and some kind of offset, right? So we're seeing that the same pattern happens over and over and over inside these examples. And I will say, if I had another panel on the left, which was the C arrays like that Björn showed before, and it's that even 50 years ago, when the designers of the C language were deciding on the syntax and the semantics of C, they could have chosen, a pointer is just a number. It's just an index inside some kind of a contiguous memory space. But someone, I don't even know who that is because it's probably earlier than the C language itself, somebody already back then understood that the semantics for pointers are different than the semantics for integer arithmetic. And the compiler saves us. So if most of us don't have problems with pointer arithmetic, but if the compiler wouldn't have caught some of these, then the situation would have been even worse. So this is such a fundamental thing, and we're so used to it that we somehow forgot this 200-year-old knowledge. Now, I want to give some counterexamples I'm going to pick on OpenCV because it's a library that I work on and with for many, many years. And it's got this class type called point, position, and it's initialized to the owl. Does anyone here not see the owl? Can you all see the owl? Yes? Okay, good. So it's initialized. And we can do the next pause is actually the addition of a point plus another point cast from a pointer. And as we said before, what does actually adding points mean? How can you add Oslo and Tel Aviv? There is no physical meaning to that operation. But in OpenCV, it works just fine because it's just a struct of two numbers and somebody overloaded the operator plus. Because the point is literally behaved just like a vector. And similarly, we can subtract 2 points, but the result is another point. It's not a vector. And you can negate a point. Again, what does that even mean? Or scale it. Now, I'm not just going to pick on OpenCV because PCL, which is the point cloud library, it's one of the probably the most popular library for working with point clouds and unstructured 3D data, also has this problem. And Eigen, which is an amazing linear algebra library, also doesn't basically totally ignores the distinction between points and vectors. However, the computational geography algorithm library does make this distinction. And you might say, well, okay, it's interesting, 200-year-old information. Okay, what's new? And how bad can this be? And all I can say is remember the Mars Climate Orbiter. This was a multi-billion-dollar project built by NASA and its contractors. And I'll just quote from it crashed after arriving at Mars after maybe 15 years of development. And the crash report says that software that calculated the total impulse produced by thruster firings produced results in pound force seconds. The trajectory calculation software then used these results expected to be in Newton seconds to update the predicted position of the spacecraft. So In this case, this is a problem of the type system not enforcing the units of the values. So they used bare, maybe integer or floating point numbers, and there was no enforcement of, no compile time enforcement of units. And the type of thing we're talking about here is very similar to a unit system, to a proper unit system. Whenever we can leverage the type system to catch type errors at compile time instead of at the point of the committee that has to investigating committee time or crash time. So now we're going to see some examples of what this might look like when implemented. So Björn, I'm going to let Björn continue.
Thank you. So, when preparing this talk, I decided to investigate a number of GUI libraries because I thought these are good examples of where you use these. So I looked at quite a lot of them. I make no claims to have investigated them all because there are many. But an interesting observation is that not a single one of those that I looked at did this right. So I'm proposing a different GUI library where in this case we have a proper distinction between points on the screen and vectors. So I have a window class and its constructor says I can construct a window at a position, a point, and its size. And the size is a vector, so we know its width and its height. And the code on the right, we see how we can do this by saying that in this case I happen to have 2 points where I want the corners to be. But since we have a proper type system where points can be subtracted to get vectors, this is not a problem because then I just say, yeah, I want my window to be on point 1 and the size is the difference between point 2 and point 1. So that is cool. And also if we want to move a window around on the screen and translate, we want to translate it with an offset. So we give a vector, say move it such and such many pixels to the right and so many upwards. And again, I can subtract 2 points to get this vector. Or maybe I actually want to move it specifically to a point. And the important thing here is that if I make a mistake and I accidentally call move to with the vector, I get a compilation error. This is good. We can actually have a look. Yeah, curious detail. This talk was actually born here at NDC Oslo last year. So Adi and I were speakers here then too, and we were talking about how we should do this. And on my way home, my flight was delayed, so I was extremely bored at the airport. So I started cranking out code. So I wrote a small mini library, which you have the URL to there. It's a C++17 library. So let's have a look at Compiler Explorer. So to begin with, did you know that you can hash include URLs in Compiler Explorer? I think that is excellent. For this example, I have a simple classic type of the 2D vector v that of the kind that Adi mentioned from the other libraries that makes no distinction between what is what. We just have an x and a y, and we have plus equals and minus equals and the infix plus and minus operators. But with this library, I can say that now a vector is an affine displacement of v's. And I use a tag to discriminate between this and possibly other types of displacements using also v, but they may represent something completely different. And then I have a position type that is an affine position of v. So you use the same implementation under the hood. And it uses the vec2d as its displacement type. curious thing. I heard a few months ago about I think it was a ray tracing program that used one three-dimensional type for interchangeably as a position in space, as a vector in space, and as a color, RGB color. Interesting. So we can have a position in space, which we add this yellow to, whatever that means. The compiler wouldn't catch it. Here we have absolutely no problems because these are now distinct types. I will show you how we get compilation errors if we make a mistake. Also, I made this library such that we can change it and instead say that I have my position and just default a displacement for me, and then I can use an internally defined type as the displacement. So we can use that one instead. That is, why not? And it changes absolutely nothing in the generated code. So with this, I can have this window class, this imaginary thing that I showed you earlier. And we can have a create function that takes the corners as individual integers. So I can create a lower left and upper right from it. And I can create a window, as I mentioned earlier, in this case, I get the size, the vector, by subtracting the two positions. And if I make a mistake and try to, if I make a mistake and try to create the window using the 2 points instead, this does not compile. Actually, it does compile for a very long time. So we get an error saying no matching function. Candidate position and size did not match. That is good. And likewise for the move, we can see how I just create a vector from these types. It's worth noting how good are you at x86-64 assembly language? How many of you were here for Rob's talk just before this one, when he heckled at Ian me a little bit about the cost of abstractions? This window translate takes a vector. How is the vector represented? It is passed as one 64-bit register, so it's cheaper than passing these two ints in, because they are in one register each. So we have a negative cost abstraction. Yay. Not just zero cost, negative cost. And it makes the code safer and more maintainable. So that's at least a double win. So don't be afraid from this is always a thing with C++ developers. It's, yeah, but what's the cost? What do I pay in terms of performance? Don't worry. It's not a problem. At least not what I have experienced. It is possible that there are situations where you do carry a cost, but I haven't experienced that. Also, this is a cool thing. C++ 20 concepts. Petter Holmberg, a guy from Stockholm, is also active in the Stockholm C++ user group. He, after hearing a preview of this talk, or these discussions for this talk, he decided to try to model this as C++ 20 concepts, and it's surprisingly succinct. So we have a concept, affine space, that takes a position, a vector, and a scalar. And we say that, yeah, the position must be regular, and V and S must define a vector space that is defined elsewhere. And with this, we say that if we have const positions and const vectors, we can have these operations that Adi showed earlier. And also, if we have non-const position, we can modify it with vectors. So it's surprisingly easy to model these things, also in future template code where you use concepts. And I think it's time for you again, Adi. Yeah.
Right. So if you go to the mathematical literature about affine spaces, there is one additional operation which is called the affine combination, which I think is very interesting. And I want to present it and mention it in our context of speaking about APIs and types. Now, the definition, remember vectors which operate, they're closed under vector operations, vector arithmetic. They have what's called linear combinations, where we can multiply a bunch of vectors by scalars and sum up the result to get a new vector, because we said vectors are closed under addition and multiplications by scalars. Now, an affine combination is a slightly more strict operation. Basically, it means that we can have a weighted sum of one or more points, and before you start shouting, hey, but you just said that we can't sum points, we're saying, well, hold your horses for a minute, because I'm going to put some conditions that allow us to do that in very specific cases, and actually the only two cases. The first case, and this is the more common case, is where the total sum of the weights is exactly 1. And in that case, the resulting type is a point. I'm going to show an example in a minute. The second case is where the total sum of the weights is exactly 0, and the resulting type in that case is a vector. Otherwise, affine combinations are not defined for affine. It's basically not a valid operation. If anyone here has heard, who here has heard the term barycentric coordinates? Okay, a few of you. So yeah, barycentric coordinates are basically the tuple of weights of an affine combination, which sum up to 1. So you might say, okay, but okay, this sounds kind of tenuous, but why is that interesting? And I'll show an example. So let's say we have this statement. If A and B are integers, what would M be? Well, it says so in the comment. It's the midpoint between A and B, right? So again, I'm ignoring truncation and ignoring overflow in this case. And the question is, when A and B, the types of A and B are pointers, what is M? Anyone? It's actually testing if you were listening. So you can see we're summing up A and B, and we cannot really sum. We just said that even the C-type system doesn't allow us to sum pointers, right? So we cannot actually sum pointers. But conceptually, if we have 2 pointers into a valid array, there is a midpoint between them. So how do we calculate that? Well, when basic math, we can rewrite that statement as A plus the difference between B and A divided by 2. So this actually uses valid affine space operations for performing, because A is a point and B minus A is already displacement, right? So, and we can multiply that by 1/2, or the equivalent divided by 2, and we can add that as a displacement to our pointer. So another way to look at this is as if we're multiplying A and B by 2 weights, which sum up to 1, which is 1/2 and 1/2, right? So this is exactly an affine combination. This is exactly the case where we want where these affine combinations are interesting. Whenever we want to find interesting points that depend on the rest of on the inputs. One very popular example is, for example, calculating this center of gravity. So let's say we have 3 points, and this is actually independent of the, not necessarily 2D points, it could be points in any dimension. If we multiply, if our weight is 1/3, then again we're getting the center of gravity of our point cloud, say. In C++20, we're actually getting a function that's designed to allow us to do that, and it's called std midpoint. And I think the main motivation is exactly the fact that you can't add pointers, and the fact that you don't want to, in this case, you want to avoid the overflow of summing. So even when you're trying to sum two integers, a plus b, if b is the maximal integer representation, you're going to overflow, and then you get undefined. You may get, well, you may not get the answer you were expecting, because primary school math doesn't necessarily work with such limited size numbers. So we're getting std midpoint, which does exactly that. Now, so to summarize, I think the main point of the talk is not just the fact that we already know affine spaces and go and look. Once you start looking at your code, knowing this, because you've already seen it before, you might try to apply these concepts to your own APIs. But I think the message is much more powerful than that. It's about creating strong APIs. It's about having this if and only if relationship between the syntax and the semantics. So whenever something compiles, it means that we got the semantics of the behavior. Semantics are behavior. Syntax is the textual representation of our code. Semantics is the behavior, the expected behavior of our code. The fact that the little arrow goes from left to right and right to left means that the inversion is also correct. So a semantically incorrect expression will always be a compilation error. And this maybe is for me, it's the most powerful message that you need. Maybe if you need to take one take home from here, is to think about these. Always try to have stronger types and a stricter type system. And affine space type relations are very, very, very common. So common that we're almost they're invisible to us. But once you point it, it's like the hammer where everything looks like a thumb. So yeah, it's the same thing. You're going to start seeing that. So we need to. We encourage you to try and identify them and build your APIs in such a way to give you this powerful and consistent abstractions. Because math has already done a lot of this foundational work for us. If you go and read a little bit more, just sometimes it's a little bit beyond what you might have studied in university. Read about abstract algebra, and there's a lot of talk and a lot of many talks online about category theory, which is getting a lot of, I think it's a very, very fruitful field for API and type design. I really encourage you to go and watch that. And as Björn likes to say, when in doubt, do what Chrono does, because Chrono is an amazingly designed library. And they got so many things right, where other libraries usually lacked some kind of abstraction. Do you have any additional closing words? Yeah.
Yes.
Yes.
On closing words, yes, I do have one thing, and that is think about context. So
yeah, right.
I mentioned very briefly when I first went through the example with pointer arithmetics that the difference between 2 pointers is an integer type, which is wrong. Because with an integer type, you can do operations that don't make sense to do with pointer arithmetics. That is, for example, you can multiply them. That doesn't make any sense. Chrono has forbidden multiplication of durations. Think about context. Does it make sense to have seconds squared? If you're writing a scheduler or a calendar program, no, it does absolutely not. so it should be forbidden. But if you're writing some kind of physics programs, you really want to be able to represent seconds squared. So think about the context where your types are operating in. That was the addition I had.
Great.
Some additional resources if you want to learn a little bit more about this. Adiv wrote a series of really good blog posts about this with a number of examples and some reason. If you're into C++ nerdery, you can watch my talk from ACCU last year. Ben Dean's talk was really good, the CPP-Con one.
Yes, you should watch it. I think affine types are mentioned only at minute 13 and 53 seconds for about 20 seconds, or a couple of minutes, but it's a great talk and you should definitely go and watch it about operator overloading in general.
And Peter Sommerlad's talk from CPP Now that came out on YouTube just a week ago or something. He's going through all these things with not just explaining how you write strong types, but also this think about context. When does which operations make sense? And towards the very end, the last few minutes of that talk, he actually goes through these affine space type combinations where the position and the displacement are, well, I wouldn't say meaningless on their own, but they don't mean a lot. But together, they do mean a lot.
Yeah, I think if anyone, I didn't see the answer before, if anyone was here for the previous talk by Robert, he talked about the architect's role, and that the architect needs to protect the principles and the design, because the features will take care of themselves. There are enough stakeholders to take care of the features. And in a way, this is exactly what we're trying to say. If you design your systems properly, you allow the compiler to catch wrong usages and catch these errors so early in the design process that nobody actually ever makes the types of errors that then may crash. Because really, to crash a spaceship on another planet because of a type error is ridiculous. I mean, there are many things that can go wrong, but a type error should not be one of these reasons. So I think we're optimistic. So we're big fans of strong type systems and static type systems, and we encourage everyone to join the revolution, the 60-year-old revolution.
200 euros.
200 euros. Yes, thank you.
Thank you very much. Yes, question.
Can I take that?
Yeah,
yes.
Sure.
The question was whether we can apply the concept. I'll repeat the question for the video and to make sure that I actually understood it. Is that whether we can apply these principles in cases where the underlying types might not be regular arithmetic types, or like complex numbers or quaternions? I would counter that complex numbers, they can be scalars, and we saw many examples of one-dimensional types that the underlying representation is still an arithmetic type. But in terms of the behavior of the type, we distinguish between something that you can do certain operations on and disallow other operations, which would make sense on the underlying representation, but not at the domain-specific representation. Does that answer your question? For example, chrono, let's say chrono doesn't do this, but hypothetically, or you can represent a time point as a single number, which is the number of milliseconds since January 1st, 1970. And you can say that the duration is just a signed integer. So these are both integers. And integers in the type system support all the arithmetic operations on integers. But the API produced by this wrapping type, actually, what it does, it disallows certain operations in order to give you the proper API to avoid misusage.
So that's what I'm aiming at. Yeah. So if I would use your library and my type has this plus operator defined and implemented, then your library wouldn't disallow me to use the plus operator.
It would disallow. It would, exactly.
So then it wouldn't be possible to use your library with, for instance, complex numbers.
Wait a minute. Were you referring to the library that I showed with the Godbolt example? Yeah, it would work. You can use that. It uses the underlying types operators. So it defines all the operations that make sense in the affine space, provided that the underlying type supports them. So you can have, in this case, I had position and displacement of this V struct, where I had defined operator plus and minus. And complex numbers support operators plus and minus, so they can be used right away, as is. More questions?
So I think the type safety thing spans like many more domains than possible, what you're specifically talking about here. So like the software that I work on is kind of biology and chemistry. So we're passing around like different units and we have to make sure that we convert them correctly. And the amount of bugs that we get because somebody's not converted to centimeters, millimeters,
Yes.
or they're not combining like a height and a weight together correctly. So we've been trying to look at ways of avoiding these bugs so that they're basically stopped at compile time. And I came across a library recently, which I think might be similar to perhaps what you've been working on. I think it was proposed for the C++ 20 standard to have like strongly typed type defs, but I don't think that's actually going ahead.
Okay, so to repeat, you're talking about you're mentioning that your problem, you're talking about you need representations for physical units, and you have several different types of units for the same kind. So you have meters, you have millimeters, you have feet if you're bizarre, and what we talked about now about affine space combinations that does not cover that. It's on a different scale.
It's orthogonal.
It's yeah, mostly. You mentioned a proposal for C++ 20. Is that the one that Matthias Pusch is working on? Okay, yeah. He presented at ACCU a work in progress physical units library, and to me it looked extremely good, but it's work in progress, so it will definitely not come in C++ 20. It will maybe come sometime later, but it's also an important thing that this presentation mentioned briefly by Peter Sommerlad from C++ Now just a couple of weeks ago. He actually goes into this and says that physical units themselves are great, but don't forget context, because in some contexts some operations make perfect sense, in other contexts they don't. So having a representation of physical units is great, but it's not enough.
But there are some excellent unit libraries, for at least for C++ that we know of, and in cases where you do get problems with mismatch, there is no reason to waste cycles or developer time on tracking these down. So do find a good unit library. I think Boost has one, and there's several other ones.
Boost is terrible. Don't use that one.
Okay, I haven't used that one.
But there is actually there is a connection between physical units libraries and what we talked about, that physical units libraries tend to fail, and that shows extremely clearly when you talk about temperatures, because you have temperature points and you have temperature differences, and doing arithmetics on temperature differences in Celsius and Fahrenheit is trivial. It's really not a problem. But doing conversion between temperature points in Celsius and Fahrenheit is where you mess up. And these libraries that I have seen tend to miss that.
Any more questions?
More questions?
All right.
Thank you very much.
for joining.